Welcome to the overview of minerals, the rock cycle, and fossils. So in our science, one of the things that we're constantly trying to do is evaluate what's out on the planet, or if we're in outer space and astronomy, looking at what's out in our solar system, galaxy, universe. But let's just start with planet Earth and examine what's here. How do we interpret what's there in terms of earthen rocks, fossils, and minerals? How do they fit together to tell a story? Because in geology and earth science, everything provides clues. And that's what an earth scientist is trying to answer, are questions about ancient life, ancient environments. Basically, why is what we see there and how did it happen? So take a look at this really cool rock. It's like one of my favorite places in terms of cool rocks in Rocky Mountain National Park in Colorado. That is one of the best specimens of gneiss that I've ever seen in the field, and it's extraordinary. The gneiss itself, you see the stripes in it. That's unusual. That happened from extreme pressure, where something, a rock like granite, most people are familiar with what granite looks like because of granite countertops. Imagine that those crystals got squashed and flattened because of heat and pressure. So you're looking at an immense amount of heat and pressure in order to do something like that. When you find a rock like this, that's a story, and you take it in conjunction with everything else around it. So if this was the only rock like it in Rocky Mountain National Park, it really wouldn't tell a story. It'd just be really cool. But there are lots of rocks like it. And that's because the area is evidence of ancient mountain building. You're like, well, yeah, there's a mountain there. Well, of course, but it tells more than that, because these rocks have a lot of clues embedded in them and in the surrounding landscapes that tell us how that mountain building occurred, about when it occurred, the conditions that might have been present when it formed, the types of rocks that already existed when these rocks were changed. Just a load of information. Almost think of it like metadata. It's like the information that we know about people now and things that you can look up on subjects, let's just say even on Wikipedia. You almost can do that in geology by simply examining landscapes and rocks, fossils, and minerals in the place that we find them. The first place to start when we're looking at rocks, fossils, and minerals is actually minerals. Minerals make up rocks, not the other way around. And so you might hear something called rock salt. Well, that's still a mineral. It's just a generic name for someone calling rock salt, which is halite. It tastes like salt, and it comes kind of in a cube or format where it's in big rock formations. That's where it gets its name. But minerals, they are the building blocks of rocks. And even minerals have building blocks known as atoms. So every mineral has its own unique special recipe of elements. And how those elements are arranged in a lattice helps us determine which mineral we have. There's over 3,800 already identified minerals, and more get added based on new information and new discoveries that scientists make. So let's be realistic. A majority of these minerals are rare. They don't happen very often, and when they do, they're kind of a big deal. But others are fairly common on the planet. In fact, there's about 30 to 40 of them that are super common that make up a majority of our Earth's crust. So I do want you to think very granular, tiny, when we're talking about minerals, and understanding that, for example, we think about sandstone. Sandstone is made up of different minerals, and some sandstone is very rich in quartz. Quartz is a mineral that is a silicate. So you take a look from left to right. Do you see that red circle? This one right here, that is silicon. It's a silicate, a silica. And those make up quartz when you have this arrangement of atoms with oxygen and silicon, and then that creates a special mineral known as quartz. And quartz, in turn, is one of the building blocks that we see in quartz sandstone. Very, very common mineral and very common rock out on the planet's surface. So when we're thinking about how minerals are made, they don't just like usually pop up, poof, and they're here. Sometimes we might get a gift from outer space where you get a meteorite that provides us some unusual elements that we don't have very many on Earth, or even more exciting, if there wasn't one that was recognizable to Earth that came from an extraterrestrial source. But most minerals are made simply through the processes of ways that we can create them. Through example, on the left picture, you see a hydrothermal feature known as a geyser. Well, the heat from that feature mixed with hot water and the minerals it comes in contact with creates some new minerals in that procedure. On the right, you see actually a place called Badwater Basin in Death Valley National Park. And those are evaporite deposits where water was standing and it evaporated and left behind solids. We can also get new minerals forming in processes of metamorphism, which you'll learn about real soon. We can create minerals in igneous processes. So the point being is that I can't talk about the rock cycle without giving you a short introduction into minerals, because minerals are indeed the thing that make rocks happen. So there are a number of ways that earth scientists identify minerals. One of the important things to think about mineral properties is you're just getting started with mineral identification. I don't expect you to be an expert. In fact, if you become a geology major, you'll usually have a couple of semesters of mineralogy. And then if you become like that's your focus, you're the expert on it, you'll be doing years, a lifetime of work in this. So here's a shot of some minerals from the Smithsonian Museum of Natural History. And while they're beautiful and they're extraordinary samples, keep in mind there's over 3,800 of minerals out there. So I chose this because these are a variety of the same type of minerals in one display cabinet in the Natural Museum of History. They're all fluorite. Well, fluorite is a very special mineral, common mineral though. And the fact that it's in all these different colors, you might need more information to identify it if you found it, let's say, out in the field. So that brings me to the most obvious of all properties of minerals, and that's its color. Color is the least dependable way to identify your most common minerals on the planet. So this is all calcite you see right here. In a minute, I'll be talking about the Mohs hardness scale, and I'll compare calcite to fluorite, since you just saw fluorite. Calcite has a hardness of 3, fluorite has a hardness of 4 on the Mohs hardness scale. They can look very similar, just like these minerals can also look like quartz. And I think it's important to realize that many minerals come in rainbows of colors. And so you can't just say, oh, because it's blue, it's always going to be calcite. That's not the case. You can't say that a sapphire is always going to be blue. So you have to know more about the mineral. There are some minerals that predominantly come in like 1 or 2 colors. So color begins to be a good way to narrow the scope, but not the only way that we can identify a mineral. Streak is a very good way to identify minerals. So there are 2 different types of streak plates. There's a white one and a black one. They're used for different types of minerals. But in essence, most of the time you'll be using a white streak plate, and they're designed for you to take a mineral and literally drag it across this porcelain plate and see if a color is left behind. So back in the gold rush days, it would have been super valuable to have a streak plate instead of people biting down on a specimen they assumed was gold. And I'm going to tell you why. I'm going to go back to that Mohs hardness. If you look at pyrite in the right picture and you see that it kind of has a grayish black, and if you get closer up, it's almost a grayish green black color. And then on the left, you see a golden yellow color for the streak of gold. And you're like, well, duh, it should streak gold because it's the mineral gold. Well, pyrite looks just like gold. And so that's why it's referred to often as fool's gold. Having said that, the hardness is radically different, and so is the streak color. And so a streak plate is an easy way to tell the difference, but a hardness test is another way that you could determine whether you had gold or pyrite, because gold is really soft, so you can actually put a dent in it with your teeth if you were to break down on it. If you were to do the same thing with pyrite, your teeth would likely break, which is my own hypothesis, is that a lot of people in the gold rush days were missing teeth, not just because of hygiene, but also because of biting down on pyrite, because it's such a harder mineral than gold. So streak is looking at a mineral's powder and the color that it leaves behind. Some streak colors are not visible to the human eye. So we might say that it has a translucent streak or a white streak. That's one reason we use a black streak plate as compared to a white one for minerals that are clear or that are white, so we can see that powder better. Mohs hardness. So hardness is one of the better properties of minerals, but I need to take a moment to tell you that hardness is not the only mineral property that we should look at. And by the way, while there are 10 slots of hardness, they are not exponentially harder from 1 to 2, 2 to 3, and so forth up to 10. So this Mohs hardness scale has 1 at the top and 10 at the bottom. There are a number of minerals that have a hardness of 1 or between 1 and 2. There are a number of minerals that have 2, 3, 4, 5, 6, 7, 8, 9. There are some synthetic minerals that are comparable to diamonds these days, but naturally occurring, diamonds is the hardest. Corundum is an example of sapphire. It's an example of rubies. And then topaz, you're probably familiar with. So you may not know what feldspars are, but you probably know what pink granite looks like. The pink is the potassium feldspar. As an FYI, feldspar is important to forming clay, which makes up our soils and helps with the life cycle on the planet for making an environment conducive to growing plants and sustaining ecosystems. So these 10 minerals that you see for hardness are 10 of our very common minerals. And you may think, oh, well, diamond's not very common. They're actually pretty common in terms of being raw materials on Earth. They just may not be diamond grade for jewelry grade type things. But I do want to say that if you had something like topaz, which is an 8 on the hardness scale, topaz would scratch all the minerals that are above it in this diagram. That'd be 7 all the way up to 1, but it could not scratch corundum, which is a 9, or diamonds, which is a 10, or any minerals that were 9 or 10. So with that in mind, it might actually scratch another topaz. But keep in mind that minerals are important because we look at them, we identify them not just for their singularity when we find them in the field because of intrinsic monetary value, but as an earth scientist and geologist, we really care about them because they help us understand environments by which rocks are made. When we look at hardness, you look at something like this. This is gypsum, so it has a hardness of 2 on the Mohs hardness scale. It was on that list I just gave you. There are those 10 standard minerals that are reference minerals, is what I like to call them, that are used on the Mohs hardness scale. And field tests can be done where, like, your fingernail has between like a 2 to a 2.5, unless you have really hard, like acrylic nails. Like I had a friend that just naturally had hard nails that were almost like a 3 on the Mohs hardness scale. But mine are more like a 1.5 to 2 because they're very flimsy. But gypsum has a hardness of 2, so even I can scratch it on a good day that I want to run my nails. And I can scratch it like you see this piece of gypsum scratched right here. I can also use a penny because a penny has like a hardness of 3. And then I can also use other tools that geologists might have, which are like a steel nail, It's just some things that geologists carry with them to try to help identify basic hardness when we find things in the field. For example, going back to pyrite and gold, I would not be able to scratch pyrite with that penny, but I would be able to scratch gold with that penny. So having a penny in your field bag, that when you're going out to do legal collection of fossils, rocks, and minerals, it's always a good idea to have that. A steel nail, which is usually around 6.5 on the Mohs hardness scale, and just a few other basic tools that are useful in mineral properties as well as understanding what you're seeing in the field. Another term that is important for minerals is something called luster. And luster is basically how does a mineral reflect its light? And that can be something from its brilliance of metallic. If you could imagine gold and then how it would shine with light on it, or you can see something that has a non-metallic luster. Maybe it has a pearly luster. You can even imagine what that looks like, or a silky or waxy. These are all terms that are used to describe luster. So in short, luster is just basically how does a mineral reflect light? Specific gravity is an important thing and topic that we look at when we're thinking about mineral properties. Here's why. Specific gravity is basically how dense is that mineral in comparison to water. Water has a specific gravity of 1. So when a mineral property of specific gravity, we're thinking about that. We're thinking about how much matter exists in a specific space. So in the sample that I have in this picture, it's literally only about 1 inch by 1 inch. And I have a zoomed in picture that I took of it. But if you pick up this sample, it is heavy for its size. That's because it has a high specific gravity. So if it's a low specific gravity, it's going to have like a 1 to 3. When you start to get into average, that's 4 to 5. When you're starting to get into something that's really dense, like 10 or more, you're starting to get into usually metallic type minerals. And don't be deceived that something that has a high specific gravity, it doesn't mean that it is a high Mohs hardness. For example, this is galena. Galena has a very high specific gravity, but it is very soft. It's like a 2 to 2.5 on the Mohs hardness scale. So it feels like lead. And you might even think, oh, well, this would hold a magnet because it's so definitely metallic. It does not. But that's why you need to look at all mineral properties in conjunction to help kind of identify what you have. So another important mineral property is something called cleavage and fracture. Cleavage is basically how does a mineral break apart. So going back to what I showed you with that galena, that was the silver one you saw just a second ago, that one broke into blocks or layers that would have really great cleavage. So cleavage describes how the mineral tends to break apart along specific planes. And there's a variety of different types of cleavage descriptions that we can apply to a mineral. But in this course, we're just trying to tell the difference between cleavage and fracture. You can see this is a piece of muscovite known as mica, and you can see that it peels apart almost into laminate layers, and it actually does. It makes really, really thin layers, and that would be just perfect cleavage. Fracture is something different. So minerals that don't break along a nice flat plane or smooth plane, they would fracture. I like to think of a bottle, a glass bottle that's been dropped, and maybe the bottom of it kind of fractures a bit and it doesn't completely shatter, but it breaks in a rough edge. That's kind of what I want you to be thinking fracture looks like. So it's different from cleavage because cleavage breaks apart in nice designated smooth sections. That is certainly not the case with fracture. So you look at the left image there and you see an irregular fracture along the edge of a piece of a mineral, and then you see a concordio fracture over here on obsidian, which is volcanic glass. They're both different types of fracture, but they don't have a nice smooth plane in which they split apart. So all minerals have some form of fracture, but they don't have to have the cleavage. In this class, I don't really think that crystal shape's the most important thing for you to be thinking about. That becomes so much more important when you have a microscope and that you're in a mineralogy course, because minerals will grow over time and they will grow and they will make a shape. I almost like to think of them as how ice and snowflakes grow. And you think about how ice starts to grow on a window, well, it makes a certain pattern. So all minerals will grow that lattice that we talked about, and it at the microscopic level you can really see this, but when you see crystals that have made large crystal form like these have, you notice that they each have a little different shape. So the crystal shape is important. That can be helpful to an earth scientist to narrow the scope of what specific mineral we're looking at. There are other special properties. For example, look at the left here. You see a piece of magnetite. You see all those magnets I stuck on it there. That piece of magnetite's literally about a foot and a half tall. It's a pretty big piece. And not very many minerals will hold a magnet. You can think about if it reacts to acid, there's only one mineral that does. It's calcite. So we talk about that as a special property. Sometimes they smell. And if they smell, that's important. Sometimes they taste. And so you might see a geologist touch a mineral maybe directly to their tongue. If you're not going to want to do that, do what I just did and put it back to your tongue. Some minerals actually fluoresce under a black light. Many forms of calcite will do that. And so they can be very beautiful and just another property to help us identify what we have. But not all minerals have special properties. And that's important because it helps us as scientists identify a little bit more about what we have. Quite frankly, a lot of your common minerals, you just need a few pieces of information to identify them. Here's another example of effervescent, which is the ability to react. On the left, I had put some diluted hydrochloric acid on this piece of limestone, and it's bubbling up because it has calcite in it. No other mineral will react. The mineral on the right is a sample of sulfur. And if you got close to this, it would smell. It stinks. It smells like rotten egg. So every special property is important when we think about everything from its color to its streak color, to its hardness, to its specific gravity, its crystal shape, its special properties, its luster, all of these things. In conjunction, we need to start looking at the minerals that are the building blocks with that in mind. So before we get into the rock cycle, I want to take a moment to just share some big groups of minerals that scientists recognize that make up most of the minerals that are common on the planet. So I'm not going to go into great detail, but I'm going to tell you by far the most common mineral are the silicates. There are two major groups of silicates, ferromagnesium and non-ferromagnesium. So you can see one contains iron and or magnesium and the other does not. The non-ferromagnesium silicates, these are the ones that are typically lighter in color and they're not as dense. And they're usually the ferromagnesium ones are darker and they're more dense. So an example might be, this is a non ferromagnesium right here. So it lacks a lot of iron and magnesium. It's lighter in color, but this one right here is a form of olivine. This would be an example of one that would be a ferromagnesium. So they're denser. So to link to plate tectonics that you'll learn about soon in this course, our continental plates are made out of stuff predominantly like this. Our ocean plates are made of things predominantly like this. So they behave differently because of their density. But silicates are very common mineral groups. The next mineral group are carbonate minerals, and these are a combination of carbons and oxygen mixed with other elements. For example, calcite, here's your classic calcite, chocolate-looking calcite, and dolomite. These are very, very common minerals that are a calcium carbonate type base thing. So carbonate minerals are often associated with marine environments, not always, but most of the time. Halides are another major group. These contain elements like chlorine and fluorine. So halide minerals like halite, which is that salt we were talking about, and fluorite, which was the first mineral that I talked about. These are both examples of halides. Sulfates are another major group of minerals. These are ones that contain sulfur and oxygen compounds and may combine with other minerals such as barite on the left. These make really gorgeous uh, looking rose petals, and they're often referred to as desert roses, or they can make some even unusual looking gypsum like you see on the right, that crystals. Not all gypsum makes beautiful crystals like this. Some are more platy, like I showed you one earlier for hardness. Sulfides are ones that contain sulfur in some type of a metal. Great example is the galena that we looked at earlier that is really dense, had a high specific gravity, and pyrite. These are both sulfides. So native elements are those which by themselves as individual minerals usually have an intrinsic or an industrial property that makes them attractive for monetary purposes. And you see copper on the left, the rock in the middle contains silver, and then you see my wedding ring on the right, which would have both gold and diamonds. So these would be examples of native elements. So the rock cycle is important as the next step in learning in this class. And I want to take a second to say, yeah, you probably learned about this at some point in your scholastic and academic journey. I'd like to take it to a whole new level of understanding. And we got to start right in the middle with magma. Magma is molten rock by definition. And oftentimes people use magma and lava interchangeably. And to a degree, I'm all right with that if you always understand that the rock cycle did not begin with lava. It couldn't have. We had to have a source for that molten rock, which was some type of intrusive, meaning inside the earth magma body that allowed that molten rock to come to the surface. So that kick-started the rock cycle. So there was a point in geologic past when the earth was basically a molten planet. And that was pretty early in its existence. We're talking about somewhere around 4.5 to 4.4 billion, with the B as in Bravo, years ago. Once we begin to cool off that, we would have had this right here. We would have had lava and then igneous rock at the surface. So we were igneous to begin with the magma, but then we got extrusive igneous rocks, which is lava. At that point, the lava would have had two outcomes. It would have been subject to forms of weathering and erosion and broken down into sedimentary rocks, or it could have undergone some type of pushing back into the subsurface at a plate boundary, which you'll learn about in plate tectonics, and gone subsurface and then been heated and possibly put under great pressure, if not both, and undergone some form of metamorphism. Or it could have been reheated again and made into a different igneous rock, either at the surface or subsurface. Point being is that each place within the rock cycle can be interchangeable. So let's look at this sandstone. This is a quartz-based sandstone. So since you just learned about minerals, that's a silicate mineral. And it's predominantly made of quartz minerals that are in this piece of rock that are a certain size in diameter. That's what makes it sandstone and not maybe like mudstone. And over time, they get deposited. Let's say we get a mountain range that has a lot of granite, and in granite is a lot of quartz, and that quartz weathers out, and maybe it's near a beach or it creates sand dunes in a desert. They deposit sand layers, and boom, you get sandstone over time. So sandstone could get melted and turn back into magma or lava, or it could undergo a temperature and a pressure change subsurface and turn into some type of metamorphic rock, or it could be weathered and broken down into new sedimentary pieces to make another sedimentary rock. It's very rare that a rock stays at the same point in the rock cycle for its eternal existence on the planet. There are a few handfuls of rare examples where they haven't changed much. And those are our rocks that are close to 4 billion years or right at the 4 billion year mark. We don't really have rocks that are terrestrial, meaning they formed on planet Earth, that are greater than 4 billion years. There's just a handful of them. The ones we do have that are greater than 4 billion years of age are extraterrestrial, so they came from meteorites. So when we're talking about the rock cycle, I need you to understand the foundation piece is that rock cycle got started by molten rock from inside the earth that came to the surface because that's what the earth was just a ball of magma. And then it turned into a ball of molten rock that had kind of a shell around it, which was the igneous rock shell. And from there, we could start to make sedimentary rocks, some metamorphic rocks, and we've been doing it ever since. There may come a stopping point to this, so that will be when the Earth no longer has a hot enough interior to create the volcanism that would create igneous rocks. And then when we no longer have processes on the surface that allow for weathering and erosion to make sedimentary rocks, or we don't have the processes that allow for plates to be pushed back into the interior of the earth and subjected to heat and or pressure to create metamorphism. So again, magma was the original starting point. So sometimes it's hard for people to imagine magma because they've really not seen an example of molten rock in their life, because we see it now with video, but for years people had to see it in still shots or videos, educational type programs. But today with modern technology, we can watch volcanic eruptions where you can see lava spraying. That's pretty cool, but you have to imagine no lava eruption can happen without one of these beneath the earth that has a magma chamber. Magma chambers often cool off and never produce an eruption. And if they do, all of this could weather on top and we're left behind with this underground mountain building could shove it up, and then we get this big gray thing here at the surface. Case in point, Yosemite National Park. In Texas, case in point, Enchanted Rock State Park. These are all examples of giant intrusive igneous bodies that cooled beneath the surface and now are exposed at the surface. Here's an active lava flow in Hawaii. So while you can see that, you're like, oh, I get that. That's easy to see. That's a lava. Well, it had to have a counterpart here in order to work. So when we're talking about igneous rocks, there are two major groups. There are those that form intrusively or plutonically. The root word pluton means just that magma body I was referring to. So plutonic and intrusive are synonymous terms, and so are volcanic and extrusive. The term EX refers to out or above, while intrusive refers to inside. So this is an intrusive igneous rock known as granite, and this is an extrusive rock that is known as andesite. And I want to point out this one has crystals. You can see that, but notice that the crystals look like puzzle pieces on the left. That's because it's plutonic and the minerals had a chance to grow up against each other like this. So they tend to be very dense and heavy in their weight compared to the same chemical, what I would like to call chemistry or margarita mix that you might see for granite has a margarita mix. That's exactly the same magmatic material that comes to the surface as a lava, known as rhyolite. This right here has an intrusive or plutonic rock that matches it, a margarita mix that's the same chemistry, that's known as diorite. And it looks very much like granite, it just has more black and white, distinctively and usually not pink. So understand that these terms mean something when you see the words plutonic and intrusive or volcanic and extrusive. That's referring to where the igneous rocks crystallized and cooled off. The chemistry of igneous rocks matters. There are 4 chemistry groups: felsic, intermediate, mafic, and ultramafic. And notice that if you're in the felsic category, you're going to have very little of the green minerals, if any, but you're going to see that most of them are going to have a huge amount of what we call felsic concentrations of minerals that are high in silica. For example, potassium feldspar, K for the potassium, quartz, so most of the percentage of these two minerals. Well, those are very silicate-based minerals. They are very light in color. And as you get into ultramafic, they become very dark, black and green. So intermediate is going to be predominantly shades of gray with maybe a tad of black as you're getting close to mafic. And mafic's going to be predominantly blackish, and sometimes it can rust into red with some green. And then if you get ultra mafic, it's going to be a dominance of black and green. It's important to note that we make felsic, intermediate, mafic a lot today. And we used to make ultra mafic back in the Precambrian eon. But we don't make it hardly at all today at the surface. We certainly can make it subsurface in the mantle, but at the surface, it's just not hot enough to make these rocks here anymore. So over time, we may not be able to crank these out even from the mantle as the Earth's interior cooled off. So one more thing about this. If I had an ultramafic volcanic eruption, let's say 1 billion years ago, it would have sprayed, made a beautiful looking eruption with lava fountains. This is going to look like a pyroclastic mess and would be absolutely devastating if you had a felsic eruption. This erupts much cooler in temperature than something like a mafic or an ultramafic. So I want you to kind of shift your thinking that hotter means it's more explosive and violent. All volcanic eruptions have violence and can be dangerous, but explosivity is really looking at how much pyroclastic material comes out, and that's certainly going to be more the case the cooler the temperature gets. All right, let's move into sedimentary rocks. These are by far the most common rocks that you're going to see probably as a person that exist on Earth because there's so much of them. All rocks can weather into sedimentary rocks and be redeposited and then ultimately go through a process which they become officially a sedimentary rock. There are two major descriptions for sedimentary rocks, those which are made of pieces of other stuff. Those are called detrital or clastic. The root word clast, C-L-A-S-T, refers to pieces of other material. And then there's chemical and biochemical rocks, which are derived from either chemical processes or the remains of ancient organisms, usually microscopic organisms, but can be plant matter like coal. So we refer to sedimentary rocks as those that are formed from processes of weathering and deposition and create new rocks that are deposited and then hardened. Weathering is the process of breaking down rock. Erosion is the process of moving those weathered pieces of rock material away. Here is an example of weathering. You see the tree growing out of rock. This is actually a form of biological and mechanical weathering known as creeping, like a creep. This, where you see all the kind of orange stains on this rock, is a form of chemical weathering, and that's referred to as desert varnish. Weathering breaks down rocks, and of course, once I get a fracture or a crack in rock, weathering can be accelerated. I would say it works much like you get a cut on your hand. It may take a while for that paper cut to heal, and if you get something in it, it's going to make that cut a little wider, or it could get infected, something like that. I'm not saying rocks get infected. I'm just saying that they can split apart and break apart easier. But when we see rocks that are missing in mass concentration, like the Grand Canyon in the middle, weathering happened first, then erosion took those weathered sediments and deposited them elsewhere. Until we start shipping all of our sediments off the planet, are we going to no longer say that deposition of those weathered sediments is not happening elsewhere? What I mean is rivers, even glaciers, even wind can pick up sediments and move them and drop them elsewhere. That's deposition. So this big giant hole we call the Grand Canyon in Arizona, it's over a mile deep and in some places 17 miles wide, and it extends for several hundred miles, almost 300 miles. It's massive, and it's only been there, from what scientists can tell, for a little less than 6 million, with an M, years. Where did all that stuff go? Well, it's made rock layers elsewhere. And that's important to recognize because these are the processes by which we make sedimentary rocks. There are stages to making sedimentary rocks. They form from deposition, which is that picking up and dropping it elsewhere. A beach is a great example. This is it is my favorite beach actually on the planet. This is the green sand beach at South Point, Hawaii, on the big island of Hawaii. And if you see that tint of green here, that's from olivine, which is the mineral that's green that we often find in a mafic igneous rock that comes to the surface in volcanic eruptions. Hawaii is not the only place that you'll find this mineral, but it's very prevalent. And that olivine's been knocked out by wave action and deposited as new sand. So as this green hardens, let's say it does, it would create green sandstone, when there is such a thing as green sandstone. So that's deposition. Compaction's where the airspace gets smaller and smaller because you're smushing it by pressure. I like to use the example of stepping on trash to make it fit better into the trash bag or the trash can. Cementation is where there's some mineral growth in between those pieces of minerals and rock material that are glued. It's the like Elmer's glue or crazy glue that keeps everything together in a rock. And then the process of hardening a rock is referred to as lithification. These steps happen for sedimentary rocks across the globe. So you are never going to have a sedimentary rock that doesn't have lithification. They all have to harden. They all go through some process of compaction, cementation, and all have to be deposited somewhere. So all of these steps must occur. Moving into the third category of rocks, which is metamorphic rocks. I'm going to tell you they're some of the neatest rocks, and they're also the least common. And there's a reason why they're the least common. There is a narrow opportunity of geologic conditions that create them. Like 99.9% of all metamorphic rocks are made subsurface, or at least in the Earth's crust at faulting. Without going into a long explanation, I can have fault zones that crunch rocks and actually pulverize them. That's a form of metamorphism known as dynamic metamorphism. But most of our metamorphic rocks occur right at the crust surface at 0 kilometers down to about 55 kilometers. I'm not telling you can have one slightly deeper than that, but it's rare. And here's why. Because once you start getting deeper than that, we hit a process of geothermal gradient, which is a big fancy set of words for how the Earth's interior gradually gets heated up every kilometer you go subsurface, and it gets so hot it starts to make magma. So metamorphic rock, you often hear people say, oh, it formed really deep inside the Earth. In retrospect, yes, when you start thinking about a 5K, yeah, 5 kilometers is a big deal. That seems like a long distance to us. But the inside of the Earth, when we're talking about thousands of kilometers to the core, it's not that far, 55 kilometers. There are two groups of terms that we use to describe metamorphic rocks, just like we had two groups for sedimentary, just like we had two groups for igneous. They're called foliated or non-foliated. Foliated doesn't mean they're always going to have stripes. It just means the crystals get arranged in a parallel manner, typically influenced by pressure. Non-foliated is more impacted by heat, so it almost looks like stained glass. The pieces aren't making a parallel arrangement of crystals. So the texture is how we describe metamorphic rocks. So I'm going to use an example of how metamorphic rocks can turn into other metamorphic rocks. So we're going to start with what we call a parent rock, which is a sedimentary rock. It doesn't always have to be a sedimentary rock, but this is shale. Parent rock is what it was originally. Gets heated and has some pressure, it turns into slate. Slate gets some more heat and pressure, it turns into phyllite. More heat and pressure, it turns into schist. That's where we form a bunch of our garnets. Gets a lot of heat and pressure, it's going to turn into making that striped or banded rock known as gneiss. So that's a foliated version. We also have non-foliated rocks, things like quartzite and marble. But either way, metamorphic rocks only form to that narrow range right in here of depth. And I really think that's an important takeaway for understanding metamorphic rocks. So the depth, as you go down a kilometer, each kilometer, you're going to increase the pressure and the overlying weight above it. And it's just like what you would think about as pressure in the ocean. You start to get so much that it's compounding. And what it can do, it creates circumstances by which we make new minerals. And there's also one more cool thing about metamorphic rocks. Most rocks have some form of fluids in them, like water. And you start to add a lot of pressure and heat, lots of cool chemistry things start happening with that water that's in there. And you can make some extraordinarily unusual minerals. And garnets is just an example of one mineral that can be formed. But we can see certain minerals that are only made in metamorphic conditions, so they're clues when you find them in rocks. Some metamorphic rocks are found in zones on the planet because these areas, especially around mountain ranges, have certain conditions by which they form very specific types of rocks. And I'm going to use this blue schist facies, for example. Facies is just a term that we use to describe a collective similar environment by which a group of rocks form. So metamorphic rocks that are in the blue schist facies have a similar story. Typically, they get shoved into the subsurface at a plate that's being subducted, but not for a long period of time. So they don't get heated up for a huge amount of time where they probably would turn into magma. But instead, they're at depths where we do find magma, but they get shoved back up to the surface because of a mountain building event. And they make really wild and unusual rocks that are associated with them. So if you're traveling and you see something like a blue schist facies and you know what those rocks are, that's a clue on the ancient conditions by which those rocks form. I do think it's important to make a note that eventually metamorphic rocks, if they continue their journey in the subsurface by that subduction, are probably going to end up being deep enough that they could form a magma chamber again. And boom, we're back to igneous. I'm not saying it's always nice, clean, and igneous to sedimentary, sedimentary to metamorphic, metamorphic back to igneous. It doesn't always work that way. You can go in any direction and stay in that one direction for a while over the rock's existence. But over the entire Earth's existence, we've had basically the same materials being, Earth materials that is, being recycled over and over again with a little few gifts that come from outer space. But reality check is our earthen materials are predominantly made by earth processes. Which brings me to the last major part of our topic today, which is the fossil record. So we talked about minerals and we talked about rocks. They are inert, they're not alive. Well, even coal was a biochemical, and things like limestone are made up of tiny little microscopic organisms for the most part. They're still not alive. The rocks are not alive. The organisms are deceased if they are chemical or biochemical rocks. Point being is the fossil record is different. So when we talk about the rock record, I'm talking about rock layers. So I had a student once who just didn't really get what the rock record was, and I asked them to draw me a picture, and they drew a vinyl record that you'd play on a record player. And I was like, well, okay, that's very obvious. And I just wasn't thinking that way. When I explained to the individual what it was, they're like, well, that makes sense. You know, I mean, just they're rocks that are at the surface make layers. And that's our existing rock record. And it's not complete, meaning I don't have all of geologic time. Some places we're missing some of that, and some places we're missing a lot of that. And the fossil record is the same. So rock layers may or may not contain evidence of prior life. It depends on how old the rock layers are, and it determines also highly determining the depositional environment in which they were made. For example, I'll probably have quite a bit of fossils in ocean or marine rocks, and I may not have as many in a desert or aeolian type environment. That's just a depositional name environment for that. So we're going to talk about what a fossil is, how they vary, some just basic fossil terms, and we're going to start with one of the most important concepts in fossils. To be a fossil, they must be older than what the geologic time scale says is the modern geologic epoch known as the Holocene. That's the last 10,000 years. Now, if you're familiar with climate change, you may know something called the Anthropocene. Anthro referring to human, another scene, which is an epoch of geologic time. It's just that the International Commission on Stratigraphy has not added this newest epoch to the time scale. Right now, anything a fossil is less than 10,000 years of age because that's the marker in the time scale that starts another geologic epoch known as the Pleistocene epoch. You may know that as the last ice age. So I'm not going to tell you that we don't call ancient organisms that were 8,000 years old not fossils, because technically they're ancient life. But we're really thinking about fossils as being stuff that are much older than 10,000 years in age. So that can include things that are everything from tiny little microscopic organisms to woolly mammoths and dinosaurs and humans. It can be seashells. It can be lots of different things. So I do need to point out again that our fossil record is incomplete. We have literally, scientists estimate that probably only 1% of all living organisms were fossilized in the fossil record. So it's very possible that things existed that we never will have a discovery of in your lifetime. There have been some massive discoveries of really weird fossils that were soft-bodied, things like the Burgess Shale. If you want to look into that, these are massive fossil discoveries that changed scientists' perspective and lenses and knowledge base about some of the animals that we just didn't know existed until we found fossils of them. That's why it's so important that we get out there and do good scientific sound research. So keep that 10,000-year-old marker in place. If you look at these pictures, which one's the fossil and which ones are not? This should be obvious to you. The ones on the left are not fossils. They're modern day seashells. They could be in about 10,000 years. This is another one of those same seashells, but it is literally probably 100 million years old. So it is definitely a fossil. When we think about fossils, there are certain ones that are so important because they're widespread for a brief period of time. So we find them in huge numbers in rock layers, but for a punctuated period of time. So I like to think of index fossils as maybe famous musicians over the years, and you think of something maybe like Frank Sinatra, or you think of Elvis Presley, the king of rock and roll. You think of maybe ZZ Top, or you think about somebody that's more recent like Prince or a current artist. They represent a designated time, and index fossils can be used that way. In fact, that's one of the things we think about them is when we find them in rock layers, they help narrow the scope of how old a rock layer is, because it's a misconception that I can carbon date all rock layers. In fact, most layers you can't carbon date because the carbon's long gone. So the process of preserving fossils is pretty extraordinary and rare. There's a lot of challenges for fossils to be preserved. So right now you're looking at a fossil. This is a vertebrate fossil of a really crazy looking, almost crocodile looking animal of a Triassic age phytosaur, and they only lived during a brief time of the late Triassic. So they're excellent index fossils because we know when they lived. But we have to own it as scientists that we don't have a complete rock record, and fossils discovery help redefine what we know about ancient life, when they lived, how long they lived, the conditions by which they lived. Fossilization often happens in a more extravagant, or should I say more profound way, large scale way, when we have a lot of water involved. That seems a little bit like an oxymoron. People are like, well, I thought water eroded things and weathered them. That can be true. You get something like a marine environment I'm showing you here. This actually would be a great place to have deposition because I don't have a huge amount of currents coming through. There's some, but I can get sediments to settle at the bottom and then get buried by new sediments on top. If I get that successfully done, the likelihood of preserving any life forms that have died in those rock layers is much higher because it slows down the ability of that organism to decay and just gets it in a rock layer. So you might get fossilization. There's also a higher chance of fossilization when you get a larger number of groups of animals that lived of the same kinds during a specific period of time, like an index fossil. And then if they got rapidly buried is another reason. There are different types of groups of fossils that we find in the rock record. There are those that have backbones, which are vertebrates. Those are that don't have backbones, which are the most common, which are invertebrates in terms of fauna. So fauna are those that are invertebrates and vertebrates, and then those also microscopically. And then there's those that are flora, which are plants. But I have to tell you, so much of our fossil record we don't account for that are really important are the microscopic ones, like this guy over here. And some of these guys are the heart and soil of oil and gas deposits on the planet. So I do want to point out that so much of what we have on our fossil record are plants and animals. So there are two primary groups of fossils that we're going to look at: body and trace fossils. Body fossils are something that used to be the part of the ancient animal or plant, such as its bones, its teeth, maybe its feathers, its plant material if it's petrified wood. So this is a body fossil of something called a rudist. It's an actual seashell, believe it or not. But you can actually see the shell itself, that it's been preserved. That would be a body fossil. The next big group are called trace fossils. So if you don't have the actual tooth or bone or shell, but you have evidence that it used to be there, that's called a trace fossil. So if you look, you will see a 3-dimension piece of something that looks like a cinnamon bun. And then you see an imprint, like you would put your hand in mud or a footprint in mud. That's the same animal that just got smushed into the mud. This is an example of a trace fossil. So we're going to look at a variety of trace fossils, and it's important to note that we got a lot of trace fossils in the rock record. So having at least an understanding that they are considered fossils, they're just not body fossils, is important because both are exciting. Body fossils are very important because they're the real meal deal. Trace fossils are kind of just they're clues. They got left there. We know they were in the neighborhood types of indicators. So let's talk about tracks and trails. Tracks are footprints. So this is a trackway for dinosaurs in both cases. This is a trail of like trilobites, for example. Trilobites look like little roly-poly bugs. They're index fossils from the Paleozoic era. So we can get trails from things like worms, snails, trilobites, where they slither or they drag something, and tracks are the footprints that are left behind. Burrows and borings. Burrows are where animals literally burrow like prairie dogs into subsurface, and then borings are where they drill a hole. That can be a predatory or a symbiotic type thing. So these holes right here are borings. So that is a very common thing to see on many fossils, are holes where something was trying to get either something out or living on top of it. Coprolites are my personal favorite of all the different trace fossils. They come in 31 different flavors, like Baskin and Robbins ice cream. We can actually get down to the nitty-gritty of what animals were eating when they had their last meal. Coprolites, while they came out of an animal, they are not considered a body fossil because they're not in the animal. They're not a bone. They're not a tooth. They are an excretion. So they are the remains of vertebrate animals. Gastroliths are rocks that get digested by certain types of animals to aid in the process of digestion. They're typically pretty smooth because of the acid juices in the stomach. Some dinosaurs use them to help in digestion, and we even see birds do this today. So while they just look like rocks, they may be gastroliths, but usually you need some more information. If you're going to buy gastroliths off of an online site, you need a lot more information before I would say they're legit. Then there are the cast and molds that I talked about. So going back to what an ammonite looked like, I showed you these two images just a bit ago. This is what half of an ammonite would look like. That's a body fossil. So the cast is a three-dimension piece where this thing would fill up with sediment, and then maybe this actual piece of the fossil is gone, and I'm left with the mud that was in all of these sutures here, or their compartments, and then it hardens into rock. Or I get this pressed into mud, I would get a mold. So cast and molds are extremely common. I personally have found a lot more casts than I have molds, and I find that molds tend to break easier than casts, but that's just from my experience. So there are challenges to preservation of rock, and especially fossils, because soft-bodied organisms like you see right here from something like the Burgess Shale, they're very rare. Vertebrate fossils are very rare because they often get scavenged at the surface. They don't get buried fast because most of them aren't in water environments. Some are. But your most common fossils in terms of fauna are invertebrate because there's so many of them in comparison to vertebrates, just in sheer numbers, and many of them also live in water. So they tend to sink and get buried fast. So quick burial's always an important aspect for preservation. And going back to just how minute the amount of fossils that we have on Earth are, that's why every fossil should be treated with respect and not thrown away. If you're not going to do something with it, leave it where you found it. All right. There are different ways to preserve fossils. There are some that are frozen. There are some that are mummified or desiccated. There's some that are preserved in amber and asphalt tar. You can think of maybe the stuff in California is the asphalt tar, if you've been out there. And then amber, we think of Jurassic Park, but they're not the only things. We get lots of bugs and insects and smaller things that get captured in tree sap. Mummification is actually a fairly common way that we can preserve fossils to where they're pretty unaltered. They're pretty much in their original state. But frozen yields the absolute best samples because you can actually get potential DNA, really good DNA, if they've been frozen, like mammoths, for example. These have direct preservation of something that's original to that animal, whether it be hair, it be blood, it be skin, it be something that's really unusual. These have very important substantial scientific value and potentially monetary value. Most fossils are altered in their preservation. So that means that the shell, the teeth, the bones, the plant material has been fossilized using some kind of process like petrification that you see here in the petrified forest. So we'll quickly look at some of these, and we're just going to do brief definitions. Permineralization is where we get something that's turned to stone, complete stone. And this right here is a plant fossil that has been permineralized. Teeth and bones can be permineralized. That's the most common way they are. But what happens is the pores of this organism get saturated with water that has minerals in it. And it basically changes its whole structure into new compounds of rock material. Petrification takes that a step further, and it deals with plants. So petrified wood actually goes down to every part of the plant cellular material and turns it into a replaced process, and that's called petrification. And petrification can actually be something gorgeous like this, or it look very white, where it doesn't look that impressive, or it seems kind of soft. It's all based on the kinds of minerals that were in the water that saturated this plant fossil, in this case a tree, and the different hardnesses of mineral and the different types of minerals change the color, the character, and the hardness of whatever the petrified wood may be. Recrystallization is super common for animals that were shelly, like mollusk, like you see right here. This is a giant bivalve. It's actually about this big. Very common here in Central Texas. But this type of preservation actually takes whatever the shell was made out of, for the most part, and turns it into a harder version than what it was when it was living. So if you found a seashell today on the beach that was brand new, it would probably be pretty soft and you'd be careful with it because it might break easily. A recrystallized shell would be a lot harder. I'm not saying you can't break it, you certainly can. It's just going to feel a lot different than that brand new seashell that got deposited on the beach. Replacements where something like this animal, which is known as, this is a sand dollar that's been replaced by pyrite. Well, you know what a sand dollar looks like and what it's made out of. So if it turns into fool's gold or that compound known as pyrite, that would be replacement. Typically, the replaced fossils that I've seen and studied over the years tend to be harder and denser than they were when if you just found them as they were before they got replaced. Carbonization is kind of cool because this is actually where you get residue that gets left behind in the rock. Back in the day where we had Polaroid cameras, you basically get something that was organic and it leaves its impression behind, and that gets the carbon and it gets sandwiched in rock. And pretty much you don't have any of that organism left. Like there's really not a palm tree, there are really not fish there with their bones. Instead, you get the carbon prints of them left behind. So I almost like to think of them as just material that shows us that that was there. It's just not the actual, for example, plant itself. Well, the plant was there where I can't pull the plant out piece by piece. I certainly can't pull out the bones of this set of fish that you see in these carbonized fossils. They're super cool though. Now, all rocks, fossils, and minerals tell us stories. So I want to talk about these in conclusion today. Let's start with the left rock. I'm actually in Oregon in a national forest, and this is something so extraordinary because it was in a metamorphic facies, kind of like I was talking about blue schist facies a little while ago. This is such a rare thing. This rock is a metamorphic rock that is so unusual that just its presence, especially when you see a bunch of it in one area, tells a scientist how that rock was formed. So it's called serpentinite. And I was so excited. I mean, the forest rangers told me where to go to look for this stuff and do some research. And I was like, oh, hot dog, I'm going. I want to see this thing. So a rock all by itself is not enough to define how an entire area formed. You have to look collectively. This rock was just one of voluminous amount of rock layers in the area that had a similar story. So why I share that is sometimes you just find a random rock or a fossil, maybe on the bank of a river. That could have just been a random deposition event. But when you start finding many of them in the same place, like you see my student on field course, this is Neely. She gave me permission to use photos, so I'm going to use this one. It's a great find. We were in Utah at a place called UDIG, and you can keep the invertebrate fossils, and predominantly they are trilobites. So she found a extraordinary sample of a trilobite, was thrilled. And there are trilobites everywhere in this quarry, which makes it so important because it tells a story about when this could have been made, the environment by which trilobites lived. So much information can be gathered by that. And you see this just random outcrop here. It's really not a random outcrop. It's a place near Hatch, New Mexico. But what I found spectacular about this was all of this stuff up here. Well, it's actually a volcanic type of rock, this whole system is. And it was a volcanic breccia, so indicating volcanic activity, and it was weathering very quickly. And so we stopped, and this outcrop extended for miles. So until we got up close enough, could we see the story in it. So sometimes you just be passing by a rock outcrop and go, no big deal, when there's lots of stories to be told in rocks. But remember, rocks are made up of minerals. And sometimes we get a lovely little gift with a fossil in there that can give us even more detail. So I'm encouraging you as you move forward to stop and look at the rocks, fossils, and minerals. If you're in a national park or a protected area like a World Heritage Site, leave it alone. Take a picture of it, look at it, but leave it there. It's not okay to take those things away from protected or locations. So make sure you know where you are when you're collecting your stuff, and you'll learn more about that later in the semester. But more to come on rocks, fossils, and minerals as we journey into our next big topic of the course. Thanks for your time. Bye.